Hello guys, in the last class we had spoken about inductive effect and its applications, though the applications are yet not complete because there are few things where inductive effect participates and contributes a lot, and that is acidity of compounds and the basicity of compounds, and that we will be discussing later after learning few more effects. Okay, so in today's class we'll be talking about resonance, but before resonance we need to understand some basic concepts or some basic terminologies which are very important to understand resonance, and that basic terminology or basic funda is conjugation. So I'll give you a small brief about conjugation, then we will go to resonance, and along with the resonance we will be completing the conjugation. Okay, so what is conjugation? Conjugation is delocalization of electron. It is a concept, or it is, you can say, it is a science of delocalization of electrons which imparts stability to the molecule, and this delocalization of electrons is associated only with lone pairs and pi electrons. Pi electrons means the pi bond. So basically the electrons which participate in the delocalization are nothing else but either lone pairs or pi electrons. It does not show any impact on sigma bond, unlike inductive effect. So in inductive effect everything was working on the sigma bonds. Here the things will work on pi bond or the lone pairs. Now the important question is, what exactly is the delocalization? So localized electrons. What are localized electrons? Electrons which are associated to one single atom and do not move from their place. Whereas when we talk about delocalization of electrons or delocalized electrons are the ones which are mobile and which tends to shift from one place to another. So basically they'll shift from one set of atoms or one pair of atoms to another pair of atoms. So basically what will exactly happen? Existing pi bond will break and a new pi bond will form. So formation of new pi bond, after breaking the existing bond or the earlier existing pi bond, the movement of those electrons which have got created or which have got released after breaking the bond, the movement of those electrons from one place to another is called as conjugation. So basically electrons actually do not move, but it looks like, when you look at the structure, it looks like the pair of electron has jumped from one place to another. Okay, so this is delocalization concept. We will understand it in much more depth by looking at example. Probably the definition will not give you the clear idea, but we will see how exactly the movement of electron takes place or the pi bond shift from one place to another. So again, let's quickly go back to the definition. Conjugation is the concept of delocalization of electrons. So basically electrons move from one place to another, which imparts stability in the molecule. How and why it imparts stability, that also we will see. It is associated, this is important, this is very important, it is associated with only pi bonds. So basically sigma bonds do not participate in conjugation. Only pi bonds and lone pairs participate, and it has no relation with the sigma bonds. So sigma bonds will remain as it is, unaffected, and those will not even get to know that conjugation is happening. Conjugation is happening only with the pi bonds and the pair of electrons. Okay, so let's see one example and understand what exactly we are trying to explain. So what I have taken is, I have taken an example, a very simple example, that is CH2 double bond CH, single bond CH2 and plus charge over it. Okay, so now when I'm talking about these three carbons, let's see how their orbital diagram will look like. What do you mean by orbital diagram? How exactly they will be hybridized and what all orbitals will be involved, that we'll see. Okay, we all know that doubly bonded carbons are sp2 hybridized carbons. So when we'll talk about the first carbon, this is, assume this is the first carbon, this is second carbon, and this is third carbon. So first carbon has made two bonds with hydrogen and one with the carbon. All three bonds are sp2 hybridized bonds. So three sigma bonds, one here, and one here. And then it has p orbitals. This is one p orbital. This is your one p orbital. And this is your another p orbital. I have shown these p orbitals using pink color so that you can easily differentiate. And these are overlapping with each other and forming a pi bond. Correct? Now come to the next carbon. Next carbon is also having the bonds with the hydrogens. So this is also a carbocation. If you remember, I have already spoken about the carbocation earlier, that carbocation is an sp2 hybridized species. When it is in the normal alkane form, then it is sp3, but as soon as it loses a hydrogen and gets a positive charge on itself, the species become sp2. So it will have 3 sp2 bonds. One is here, one is here, and one is here, all the 3 sigma bonds, and then it will have a vacant p orbital. Now one thing which you have to understand is these p orbitals which are forming pi bond, or which is the vacant p orbital, all these are in the perpendicular plane to the other bonds. So basically, if all these carbons and hydrogens in let's say this plane, basically this plane, horizontal plane, then your p orbitals will be on the vertical plane. So all these p orbitals will be perpendicular to the plane of the sigma bonds. Your pi orbitals, the p orbitals which are forming pi bond, and the p orbital which is present on the carbon, which is empty, is also perpendicular to the plane of the sigma bonds. Okay, let me just show you this over here as a 3D structure. So this is my 3D structure. All of you please look at it very carefully. This is my 3D structure. This is my first carbon, okay, which has 2 hydrogens attached to it. So look at it. These are on the horizontal plane. Okay, all of you can see this is the horizontal plane. This is my p orbital, and this is the another p orbital which will be forming a pi bond. So this is on the perpendicular plane, right? Now look at the third carbon. Look at the third carbon. So this is my third carbon, which is carbocation. Look at this. This is a carbocation. Okay. So here again, these hydrogens are on a plane, are on a horizontal plane, and this is on the vertical plane. So we generally say this is on a plane of a, this is on the, if this is on the horizontal plane, your p orbitals will be perpendicular plane. So p orbitals which are present on the carbons to form pi bond, or the one p orbital which is empty, all these will be perpendicular to the plane of the sigma bonds. And there is no other concept in it. I mean, this is simple. You can draw the structure and you will get to know it. This is the orbital diagram. This is the orbital diagram of your molecule. This is the orbital diagram. Okay, I have drawn it in 2D. This is your 3D structure. You can see this. Okay, so here what we can see are p orbitals which are forming pi bonds are perpendicular to the all sigma bonds, and again your p orbital which is empty is also perpendicular to the sigma bonds which are present between carbon-carbon and carbon-hydrogen. Now what else can we observe over here? All these p orbitals, no matter we are talking about the empty p orbital or we are talking about the p orbitals which are forming pi bonds in carbon 1 and carbon 2, all these are parallel to each other. So they all are in exactly same direction. They all are vertical. They all are perpendicular to the plane of the sigma bonds. They all are parallel to each other. Okay, so this is the ideal condition which is required for conjugation. So what we require in conjugation, we require p orbitals on the atoms which are involved in conjugation. Secondly, those p orbitals must be parallel to each other. Then only conjugation or movement of electron from one place to another takes place. Movement of pi electrons or movement of lone pairs take place from one place to another. So it is mandatory condition for these pi orbitals, no matter the ones which are involved in the pi bonding or the empty p orbital or the filled p orbital. All these p orbitals which we are referring to should be parallel to each other. Now I hope you know how the p orbital on this carbon is empty. If you look at the hybridization of carbon, it is 1s2, 2s2, 2p2. I can draw the structure like this, as in this is my hybridization for 2s2 and 2p2. Now when it has to hybridize, it will basically shift like this. One electron will shift here, one here, and one here. So this is how the electron will shift from 2s to 2p, and then they'll hybridize and then they'll form sp3. But when I said this is CH2 plus, that means one electron is lesser. So that means I have what kind of thing? I have just 3 electrons in total, or you can just write it like this. You can write it as this and this. So this one electron of s will jump to p, and the new orbitals will become, not new orbitals, basically new configuration will become like this, and these orbitals will mix up and hybridization they'll do. So the kind of hybridization they're going to do is sp2 hybridization, and one p orbital is empty. That exactly is this p orbital. Okay, so I hope you know hybridization concept very well, and this is how the vacant p orbital is forming. Okay. Okay, what all conditions we have discussed just now? The p orbitals which are involved in pi bonding are in perpendicular direction to the plane of the sigma bonds, and the p orbital which is empty, that is also in the perpendicular plane to the sigma bonds, but all of these p orbitals are parallel to each other. And this is very important condition for conjugation to happen. So p orbitals should be in the perpendicular plane to the sigma bond, and all the p orbitals must be parallel to each other. So now what exactly happens? Passing the pass. This happens when you talk about conjugation. So two carbons have a pair of electron, they pass it to the next carbon. This exactly happens in the conjugation. How does it happen? Let's see. So here we have one pi bond between carbon 1 and carbon 2. Please look at here on the orbital diagram very carefully. So this is my pi bond, okay. It has formed by sharing one electron from each carbon. Okay, sigma bond, as I mentioned, remains untouched, and we are not going to talk about sigma bond at all. So the pi bond which is forming has one electron of carbon 1 and another electron of carbon 2. Look at the carbon 3. Carbon 3 has an empty p orbital. And because of that it has a plus charge. Okay, so any plus charge species or a negative charge species is not stable, and it will always try to stabilize itself. How can it stabilize itself, or how will it try to stabilize? It will try to reduce its positive charge, or it will try to minimize its positive charge, or it will try to reduce the intensity of the positive charge by doing some or other thing. So what it will do, basically the third carbon will try to form a bond, or will try to form a pi bond with carbon 2 by taking its electrons. But does the carbon 2 has free electrons? No, all the bonds, all are bond pairs right now, no matter they are in the sigma bond or pi bond or whatsoever, but all the electrons are involved in the bonding. So to stabilize the positive charge, what exactly is going to happen? The pi bond is going to break. Okay, so pi bond will break in such a way, that the electron density will shift towards the second carbon. So basically right now carbon 1 and carbon 2 were in the shared mode of electrons. Basically the pi pair of pi electrons had one electron of one carbon and another electron of another carbon. Now, but the bond split I told you can be of two types. One is heterolytic and one is homolytic. So here heterolytic bond fission will happen, and the carbon 2 will pull the electron density toward itself. This arrow represents from where the electron moved and where it went. So it has tail and it has arrow. Arrow represents where it is exactly going, and tail represents from where it started. This is how we always represent the electron shift. You have to understand this very, very carefully. So this arrow represents the electrons moved from here and went to carbon 2. Okay, so bond breakage happened. Electrons moved between electrons which were present between carbon 1 and carbon 2 forming pi bond are moved towards carbon 2. If that will happen, then what will be the situation? Look at this. Look at the look at the compound I have written down here. So this pi bond has moved, or the pi bond is broken, and the pair of electron has shifted to carbon 2. It will do what? It will give a pair of electron to the second carbon, and the first carbon will become what? It won't have its own electrons. It will get a positive charge. So it will get a positive charge over here. Second carbon will get a negative charge, and the third carbon anyways had a positive charge. So this is an intermediate state. Okay, which is pretty much not stable. Okay, even the first species and the last species is also not stable, but the intermediate one is further not stable. Okay, now carbon 2 is the deciding part. It can either give its pair of electron to carbon 3, or it can share its pair of electron, because of which it is getting a negative charge on itself. It can share it with carbon 3 and form a pi bond. Okay, or it can again give that pair of electron to carbon 1 and form the pi bond. If it will give its electron to carbon 1, basically if it will share that pair of electron with carbon 1, then we will again go back to stage 1. There is no difference. The bond broke between carbon 1 and carbon 2, and carbon 2 again formed a pi bond with carbon 1. So is there any difference between first compound and the compound formed after 2 giving electron density between carbon 1 and carbon 2 and forming a pi bond? No. So basically if carbon 2 decides to share the electron with carbon 1, then we will get the compound 1 itself. But if it plans to share the pair of electron with carbon 3, then what will happen? Then the positive charge what carbon 3 was carrying will get nullified and a pi bond will form. This is negative, carbon 2 is negative, carbon 3 is positive, the pair of electrons sharing will happen and the pi bond will form, whereas carbon 1 will get a positive charge on itself. So what happened? Carbon's 3 positive charge got nullified, new positive charge got created on the carbon 1. So what we can actually see here, we can see that the form 1 got changed into form 2. Right? Now here, if you try to understand this, this is exactly what we say delocalization. So pi bond was present between 1 and 2. It got shifted between 2 and 3. So we basically say that the pi bond is moved from 1 and 2 to 2 and 3. So this movement of pi bond is exactly called as delocalization. It actually didn't move. It broke in such a way that the electron density come to the center carbon and the center carbon is sharing that electron density with carbon 3 and forming a new pi bond. So existing pi bond is breaking and new pi bond is forming. And it looks like, when you look at the molecule, it looks like the double bond has shifted from its one place to another. This is your conjugation. So basically it is passing the electrons. There was electrons between carbon 1 and carbon 2. Carbon 2 got the electrons and then it started sharing it with carbon 3. So basically passing the electrons is the process which is happening in the conjugation. So I hope you would have got some idea over here. Now let's understand a few important points related to this conjugation, what we have understood. In conjugation, the atoms which are involved must have the p orbitals and all these p orbitals should be parallel to each other. And all these atoms should be planar. Basically, they should be in the same plane. They cannot be in the different plane. If they'll be in the different plane, then p orbitals are not gonna be parallel to each other. So all the carbons or the atoms involved in conjugation must be in the same plane. Your p orbitals must be perpendicular to the sigma bonds, and your p orbitals, all the atoms which are involved in conjugation must have p orbitals, and all these p orbitals should be parallel to each other. Then only conjugation will happen. Then only they can pass electron. Okay, if the directions are different for the p orbitals, they cannot pass electron. The electron density cannot be passed from one place to another. So let's see the important points now. Important points is atoms participating should be planar, as I have mentioned. P orbitals must be present with the participating atoms. So they should have p orbitals in them, and these p orbitals must be parallel to each other. These are very, very important conditions. Now, the pi bonds and lone pairs, if there are lone pair presence or the pi bonds present, they are interconvertible. What do you mean by interconvertible? Lone pair can form a new pi bond and the pi bond can be broken as a lone pair. So these are interconvertible. Your lone pairs can get converted into pi bonds and pi bonds can get converted into lone pairs. These are interconvertible in each other. So that is the reason why we take the lone pair as the pi electrons. Also, when we check the aromaticity, if you remember, we have done it in the beginning of the nomenclature. I had given you a slight idea, and that time we were wondering why lone pairs are being considered as pi electrons. So that you will further understand when we'll see many examples, and you will exactly see in front of you how lone pairs can form the pi bonds and how pi bonds can become the lone pairs again. So lone pairs and pi bonds are interconvertible. There is no participation of the sigma bond. So we won't do anything to the sigma bond, nothing. We are just not going to break any sigma bond. When you're talking about atoms or sigma bonds, their positions are not changing. Atoms will remain as it is wherever these were. Okay, so atoms are not going to move from their positions. Only thing which is going to move is the pair of electrons, no matter they are pi bonds or these are lone pairs. Only these can move. Apart from that, nothing else will move. So only pi bonds position can change, lone pair position can change, sigma bond will remain as it is, all other atoms will remain as it is. They will just not move from their position. As simple as that. These are few important conditions when conjugation will take place, and these all things we have to take care when we are talking about the conjugation or when we are dealing with conjugation. Okay, so this is about a small brief about conjugation. We will be getting indulged into conjugation in much more detail with many examples. But this is just a basic introduction to understand resonance, so that when I'll use the term conjugation, you should know what exactly I'm talking about. Okay, so let's start with resonance, and resonance and conjugation will go hand in hand, and we will see the application of conjugation in resonance and what exactly is resonance, what all conditions are required. Resonance is associated with conjugation, and it is the concept which is derived from conjugation. So you cannot understand resonance unless you understand the conjugation very well. Okay, so now let's begin with the resonance. We have understood conjugation now, a bit of conjugation, a bit of basic understanding of conjugation we have got, and now we will understand resonance. Before we start with resonance, I'll show you the structure of O3. All of you guys would have done in chemical bonding what is O3, how is the structure of O3. So this is what the expected structure is, where oxygen has made a double bond with one oxygen, and then there is a coordinate bond between one oxygen and another oxygen, and which can be represented by minus and plus also. Okay, so there are three oxygens, all are equivalent oxygens, basically not different from each other. So you can write this structure like this. If I mark this as oxygen 1, 2 and 3, this is how it can be written. And again, let's mark it 1, 2 and 3. So double bond can be between second and third carbon also, and double bond can be between first and second carbon also. So basically, this double bond keeps shifting from second to third position to first and second position. So this is moving double bond. Okay, and how did we got to know about this moving double bond? We got to know because when we actually saw the bond length and the bond order, and we saw the reactions how O3 performs. So it is actually like three oxygens are bonded with pi bonds on both the ends. So basically these three oxygens have partial double bond character. Partial double bond character means even first oxygen, second oxygen and third oxygen, all the three oxygens tend to show the bond order, not exactly a single bond, not exactly as double bond, but somewhere in between. So bond order shows that neither these are proper single bonds nor these are proper double bonds, they are somewhere in between. Okay, so that means what structure we are expecting, that is not the actual structure. The actual structure is a little different from it. That means neither the bond is single bond nor the bond is double bond. The compound, the oxygen bond is somewhere in between, and you will also find that the center oxygen is generally a slight positive or electron deficient, whereas the first and third oxygen are slight negative. That means they have slight extra electron density. So these were few things which were observed when we saw the O3 molecule. I mean, when we draw the O3 molecule, it looks a little different, and when the properties we see, the properties comes out different. Or you can say the kind of arrangement, bond order, bond length we check, the actual calculations show something else, and our understanding, our theory hybridization understanding shows us something else. Okay, that means there is some gap in our in theory and the practical application, or the practical structure or the actual structure is little different from what we expect it through the simple hybridization concept. So our theory is not well equipped to explain why the actual bond order comes different, though according to the formula, double bond either exists between first or second or third. Okay, there were few things which came into the picture, and we saw a little difference from what we expect and what is actual behavior of the molecule. Similar way, there was one more very detailed studied compound is benzene. I mean, the benzene was the compound through which resonance gets the clarity, or the concept of resonance got a better clarity, and this was the most studied compound. In fact, benzene is the compound for which almost 400 structures were proposed by different scientists. Okay, so the study on benzene started in 1780, and almost like approximately 150 years, and 1930 we got the structure of benzene. How there were many different scientists who had given us the different structures. For example, if you see here, I have shown the diagram. There is one structure given for benzene. This is this one. This first structure was given by Claus. The name is little weird. It is Adolf Karl Ludwig Claus. And then second structure was given by James Dewar. Third structure was given by Ledenberg. Fourth structure was given by Armstrong, and the fifth structure was given by Thale, which was almost right. The Thale structure was almost right. He had a little advanced imaginary thinking, and he said there are no fixed bonds. The bond seems to be moving, but he could not explain how it is possible and why it is possible. So that is why his structure was also rejected. And the last person who had given the structure was Kukel. The benzene structure what we use and he could explain the different structures exhibited by benzene, basically this and the alternate structure, or you can say it's resonating structure, he could explain, and that's why this structure was widely accepted around in 1930. Okay, so there were many scientists who actually who had actually put their hand in knowing what is benzene, and due to the actual appearance looks different, or actual bond order looks different, or reactions look different than what they imagined as a structure, all the structures were cancelled out, or you can say were rejected, because they were not giving the proper explanation for the behavior of benzene. Okay, so that means now also, what is resonance? Resonance is the phenomena where the molecule tends to show through the theoretical knowledge what we have, or the hybridization knowledge we have. We draw certain structures, but actually all those structures are the imaginary structures. They may be able to give you the explanation of some reactions, but not all the behavior of the molecule. And the actual structure is the mix of multiple structures what a compound can get converted into. It is like a molecule's pi bonds are moving in conjugation, or you can say delocalization of pi electrons is happening in conjugation, because of which it is acquiring different structures. All those structures are possible at an instant of time, but not remain in that particular form. When we are saying that all those structures are possible at a particular instant of time, at that time they tend to show a certain behavior, then they move to the different structure and they tend to show a different behavior. So individually all these structures are the imaginary structures what we can draw through our theoretical knowledge. But any structure what we can draw on the paper or can prove through the hybridization will not give you the complete explanation of the behavior of a molecule. So we combine all the structures, we basically make a hybrid of all the structures, which is called as resonance hybrid, and that structure gives you the real picture, but this cannot be proven by hybridization. So actual structure cannot be explained through our theoretical knowledge of hybridization, and the structures which can be explained through the hybridization do not give you the complete information of the molecule. This exactly is resonance. Okay, so let's see further little more details. So as I said, Kukel had given us the structure like this, and which could be written as like this. Right now, when actually the bond order and bond length was checked for benzene, what all data we retrieved? Let's see. If you talk about carbon-carbon single bond, the length should be 1.54 Armstrong. Double bond 1.33. But when we saw the bond length in the benzene, basically carbon-carbon bond length, when we saw in benzene, the bond length came out to be 1.39 Armstrong, which is neither the single bond length nor the double bond length. That means the bond is neither completely single nor completely double. Exactly same way, when we calculated the bond order for single bonds is 1, bond order for double bonds is 2, and bond order for triple bonds is 3. But the bond order for benzene came out to be 1.5. That means it is somewhere in between single bond and double bond. It's neither the complete single bond nor complete double bond. So it is somewhere in between. But how will you explain it through the hybridization? How will you show that your molecule is possessing a bond which is in between single and double? So our theoretical knowledge is very restricted and limited to explain the behavior shown by benzene. Okay, one more evidence for resonance I can show you. So let's say I have this molecule, we call it as buta 1,4 diene. Sorry, 1,3 diene, not 1,4, my bad. 1,3 diene. Okay, what we did, we took HBr of 1 equivalent. 1 equivalent means only 1 mole of HBr, very limited quantity of HBr. That means it is limited enough to just break 1 pi bond and get added over there. It is simple addition reaction of hydrogen and bromine on a double bond, but it is in a very limited quantity, so it cannot break all the pi bonds and get added. It will be able to break only 1 double bond. Okay, so okay, fine. If it can break only 1 double bond out of 2, we will just break 1. So hydrogen and Br first of all will break down into H plus and Br minus. Now H plus will go to the carbon. Let's say if I target the first double bond, Then H plus will go to the first carbon and Br will go to the second carbon. Why H plus will go to the first carbon and Br will go to the second carbon? That is a different concept altogether, which we'll be learning in mechanism. Basically, hydrogen goes to the carbon which has more number of hydrogens, and negatively charged part will go to the carbon having lesser number of hydrogens. So negatively charged part here is bromine. Okay, so Br will go to the second carbon, so it will form CH2H, CHBr, single bond, CH double bond, CH2. So this was the product we expected, and actually this product was there in the reaction mixture. So when we saw the reaction mixture, or when we saw the product, this product was present over there. What is the name of this product? This product is 3-bromobutene. Correct? So this product was present, but apart from this product, we saw one more product present over there, and that was the hydrogen present on the first carbon and the Br present on the second carbon, and the pi bond which we expected to be between first and second carbon, now it was present between second and third carbon. How did it happen? How did we got this compound? Basically, my compound had only two double bonds. One is in the position 1, 2, 3 and 4, and in this pair we had added HBr, so other should have remained as it is. How did this double bond shifted and came between second and third? This particular different product which we got had given us some idea that there is something which we are missing. There is some information which we are definitely not being able to retrieve, and there is some behavior changes happening in the molecule, some rearrangement is happening in the molecule, because of which this second product is forming, and surprisingly this product was more in quantity. Okay, so what exactly had happened? Let me just show you. So we have just now understood conjugation, so now I think you'll be able to relate it much better. So assume this is, I'm just drawing the orbital diagram. This is my carbon, hydrogen, 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 carbon and hydrogen. So this is my chain, and now let me just draw the pi bonds. So this p orbital, which is in perpendicular to the plane of the sigma bonds, will form a pi bond between carbon and carbon, and then another also will have a p orbital which will make a pi bond between carbon and carbon. Okay, so now what would have happened? Let me show you. So these are two pi bonds which are on the alternate positions, and they are parallel to, the p orbitals are parallel to each other. Now what would have happened is the bond would have broken in a heterolytical manner. Okay, heterolytical manner as in this bond would have broken, let me just show you with a different color. This bond would have broken in such a way that, assume this is carbon 1, this is carbon 2, this is carbon 3 and this is carbon 4. Carbon 1 would have got the whole density and second carbon would have got a positive charge. Exactly same way, the bond would have broken for third and fourth also. Okay, so what would have happened? Third would also have gained electron density, and the carbon 4 would have got a positive charge. So basically bond breakage has happened, and I told you in conjugation what exactly happens. The existing pi bonds break and new pi bonds form. So this would have got converted into, let me rewrite it. This is my molecule, no change in the sigma bonds. And whatever change is happening, it is happening in the pi bonds only, or p orbitals only. These are the p orbitals. Now bond split has happened. So this carbon has got a pair of electron and a negative charge, whereas this carbon has got a positive charge. This again has got a negative charge, and this has got a positive charge. Okay, now this positive, now second carbon's positive orbital and the third carbon's negative orbital, or you can say positive charge on second carbon and negative charge on third carbon, they can share, you can say third carbon can share its electron density with the second carbon and can form a pi bond. If that will happen, then what exactly is gonna happen? Let me just draw everything on a plain sheet so that you'll be able to understand. So if this will happen, then the molecule will look like this: CH2 minus CH, CH double bond and CH2 plus. This is what it will form. So earlier I had CH2 double bond CH, single bond CH, double bond CH2. The bond split happens in this way, in a heterolytic manner. This carbon got a negative charge, this carbon would have got a positive charge, second carbon, third carbon would have got negative charge, and the fourth carbon would have got a positive charge. And the positive second carbon and the negative third carbon had shared the electrons and formed a pi bond. A new pi bond has formed over here. This is a new pi bond. Correct? And the first carbon and the fourth carbon has got a negative and positive charge. Right? Now if HBr will attack on it, HBr is actually H plus and Br minus. So no extra effort HBr has to do to break a pi bond and then get added over there. H plus can go to the place where negative charge is. Simply it can go over here, and Br can go to the place where there is a positive charge. So this will become what? This compound will become CH3 single bond CH double bond CH CH2 Br. Won't it become like this? Isn't this the exact compound what we were looking for? This is exactly the same compound. And how did we get it? Basically, the shifting of the pi electrons happened from one place to another in the conjugation, where all the p orbitals were parallel. They just shifted from one place to another. Okay, old bonds got broken, new bonds formed, and a new structure got created, and that structure had given us this product. So basically, my molecule does exist in this form also, and it also exists in this form. So this is form 1. Okay, and this is form 2. This is form 2. So if I'm talking about my buta 1,3 diene, neither this structure is a complete structure for buta 1,3 diene, nor this structure is, because one part of the reaction is being shown by this, or you can say one product is being given by form 1 and another product is given by form 2. That means form 1 and form 2 are interconvertible. They are converting into each other. When it is form 1, it is forming first product, and when it is in form 2, it is forming second product. So basically they are interconvertible. Form 1 is getting converted into form 2, form 2 is getting converted into form 1, and this is being in equilibrium. So neither I can define my buta 1,3 diene using the form 1, nor I can define it by form 2. Both of these forms, I can write them on the paper because I know hybridization, because we learn single bond, double bond, triple bond only, and we can show them. We can prove the hybridization through this. But actual structure is little different from this. Actual structure which is exhibited by the molecule is little different, which would be able to explain all type of reactions, but the only problem is we cannot show it on the paper, or we cannot show it, or we cannot prove it through the hybridization. So what will be the actual structure for this? Actual structure for this is, let me write both the forms again so that you can relate it better. CH2 double bond CH single bond CH double bond CH2. This is form 1. We also call it as resonating structure 1. Resonating structure 1. Okay, and because it is converting into a different form now, this is called as resonating structure 2. This double arrow means they are interconvertible into each other. Second can convert into first, and first can convert into second. So this is my resonating structure 1. This is my resonating structure 2. Both are imaginary structures. Both actually do not exist, because if I'll say my buta 1,3 diene has this structure, it won't be able to explain you all the properties. Neither the second form will be able to. But I can combine both of these forms and can write a structure which you cannot show through the hybridization, which you cannot prove, but that structure will be able to explain all the reactions and all the behavior exhibited by buta 1,3 diene. So what is that structure? I will just write CH. As I mentioned, our sigma bonds are not affected by resonance. So according to the first structure, I have a double bond between first carbon and the second carbon. So I am not writing the whole double bond. I am just writing a dash dash dash. Similarly, I have a double bond between third carbon and fourth carbon. So let's write it as a dash 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 over there also. Okay, and then there is, according to the structure 2, there is a double bond between second and third. So let me write a double bond between this and this also. So everywhere double bond I have shown through dash dash dash. That means it is representing double bond is not fixed at one position. It was at 1 and 2. It moved to 2 and 3. Then it was there on the 3 and 4 also. So it shows that the double bond is traveling throughout. Okay, I could have a different structure for this. Resonating structure 1, 2, and third structure also I will explain you so that you are not left with any confusion. Basically, these bonds moved like this. The bond broke heterolytically and electron shifted to first carbon and the third carbon, and that's how resonating structure 2 formed. But if I would have taken it as again, let me mark first carbon, second carbon, third carbon, fourth carbon. It can also do shift other way around. So shift can happen this way also. Basically, the electrons are breaking heterolytically. Here there is no such condition why it is breaking in a certain manner. It could have broken this way also. Basically, fourth carbon could have got a negative charge and the first carbon could have got a positive charge. It won't make any difference in the molecule. I could have written it this way also. It doesn't matter. I take this compound or I take this compound. Does it make any difference to my molecule? It doesn't make any difference. It's the same thing. Now, assume this is the resonating structure 3. Resonating structure 3. So double bonds are shifting from first. Double bonds are present. If I include all the resonating structures, double bonds are present everywhere between all the carbons. So I have just shown that double bond through the dash 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 thing. Now, according to the resonating structure 2, there is a negative charge on first carbon. Resonating structure 3, there is a positive charge on the first carbon. According to the first structure, there is no charge. Basically, second structure and third structure are showing 2 different charges. So basically, they are nullifying each other. According to the second structure, there can be a negative charge. According to the third structure, there can be a positive charge. So I'm not writing any charge because all the charges are nullified. No charge on the first carbon. Similarly, no charge on second and third carbon. Similarly, no charge on fourth carbon. So this is the actual representation of my molecule. This is a structure which can explain all the properties of buta 1,3 diene and what all different products it is forming can be explained through this particular mixed structure, and this mixed structure is called as resonance hybrid. So we call it resonance hybrid, represented by RH, and this is the real structure. This is the real structure, but you cannot show it through any way. Our theoretical knowledge is so restricted, or it is so straightforward that we cannot explain or we cannot show it through the hybridization. But we know this is gonna be the actual structure which will be able to explain all the properties. Resonating structure 1, 2, and 3 will be able to solve only half of the problem, or may be able to explain you only some properties of the compound, but not all. Okay, so that I hope you would have got a slight idea about what is resonance and what is shifting of bond, and what is resonating structures, and what is resonance hybrid. And I had given you this evidence also to prove that resonance does exist, and this is what is the imaginary structure what we draw are not giving the complete information of the molecule. Instead, the resonance hybrid is. We also call them real hybrid. We also call them resonance hybrid. Either way you can call them. Okay, so let's see the old slide what we were discussing earlier. So we got it. What is resonance? We got details of the support of resonance also through one example. So we will be seeing such multiple examples. I mean, our whole organic is basically on resonance, and there are so many concepts which you are going to understand. So you will get support for resonance in multiple different areas, but this was one of the reaction I wanted to show you. Though you need not to remember the reaction right away, but this is a very good information to let you know that what is resonance, how it can impact your products forming. Okay, so if I talk about resonating, so I told you these structures which we draw on paper are the resonating structures which are not real, but the resonance hybrid which is mixed, which is formed by looking at all the structures and then compiling it into one structure, that is called as resonance hybrid, and that is the actual real structure but cannot be explained through the hybridization. So for benzene also, as I mentioned, benzene has these double bonds, three double bonds at the alternate position. I can write this as form 1, and I can also write it as form 2. Both of these structures you can see are very similar to each other, only the positions of double bonds are changing. So we call it as structure 1, resonating structure 1, and this is my resonating structure 2. Right? Both of these structures are imaginary structures, not the actual structure of benzene. We also call them canonical structures. So how does a resonance hybrid looks like for benzene? So benzene, as I mentioned, have alternate double bonds, and I can draw 2 different kind of representations for resonance. This is one representation, another this representation. So if I have to club both the forms and form one resonance hybrid, how will I do this? First structure shows that the double bond is between first and second, third and fourth, and fifth and sixth. Now if I talk about the second molecule, the double bond seems to be between first and sixth, fifth and fourth, and second and third. So basically double bond is everywhere. No matter you talk about the first compound or second compound, if you combine both of these structures, it shows that the double bond is existing everywhere, and that is the reason why we put a dash round. That means the double bond is rotating, converting from one form to another, one resonance structure to another resonating structure, and that is represented by dash. That means all the carbons which are present in benzene are experiencing the double bond, and this is the real hybrid or resonance hybrid. And this is the actual structure of benzene instead of this or this. Instead of first structure or the second structure, your resonance hybrid is the actual structure, which can explain all the properties of benzene. But if you individually take the structure 1 or structure 2 and tend to choose this is the right structure and let me explain all the reactions using this structure, it won't be possible. Only this structure can give you the details and explanation for every possible reaction of benzene. Okay, so I have written it the same thing over here. When a molecule can be taken, so what exactly is resonance? When a molecule can be taken into two or more structures, or when we can draw two or more structures for a molecule in which all are imaginary and give partial information about the behavior of a molecule, but the real structures cannot be either shown or drawn or explained through the hybridization. The real structures are a little different from what we draw, and these cannot be shown and probably may not be very useful. While writing a reaction, you cannot show the reaction over there. For showing the reactions, you need the imaginary structures only to prove a particular type of reaction. So all the resonating structures are right. We are not saying these are wrong, but these are imaginary, or you can say these give you half-baked information, so they will be able to explain you certain reactions, not all of them. And when we have to show those certain reactions, we have to take those imaginary structures only to explain. Resonance hybrid or real hybrid will not be able to explain on paper all the reactions, but give you complete information about the molecule. Okay, this phenomena is called as resonance. Now, what all different characteristics are there for resonance? Let's quickly brief. Resonance hybrid or real hybrid, you can call it anything. Different books have different words used for it. I'm writing real hybrid, you can write resonance hybrid also. So these structures tends to give the real structure, as I'm mentioning again and again, and they have the lowest energy and highest stability. Lowest energy, see, when the molecule has a lower energy, then only it will be maximum stable, and your real hybrids or resonance hybrids tends to show the lowest energy, and hence these are highest stable. Why they have lowest energy? We will come to it. We will come to it when I'll show you the charge segregation, when I'll show you when we are clubbing different resonating structures, the real hybrid is being formed. At that time, I'll explain you why your actual structures which you are drawing on paper and the real hybrid or resonating hybrid has difference in the charges and charge separation, and how your real hybrid is actually having lower energy as compared to resonating structures. Resonating structures are imaginary and are called contributing structures. Why we call them contributing? Because not all of them are giving you complete information about every reaction, but individually they are giving you the information about some set of reactions or some set of behavior of that molecule. So these are actually contributing structures which help you in understanding the molecule's behavior towards a certain reagent or physical properties or chemical properties and so thing. So they individually contribute a lot in the properties of a molecule, but one particular structure will not be able to explain all the properties. It will tend to explain certain set of properties, and when it is explaining certain set of properties, it is contributing in explaining those reactions. So that is why these structures are called as contributing structures. Next is resonating structures. RS means nothing else but resonating structures, which contribute less, is a minor contributor and with more energy and less stability. So as I mentioned, we can have different type of structures for a particular molecule. We can form different structures, two or more than two structures can be formed, and as I mentioned, all of them are imaginary, but not all of them have same energy. Some forms which will have more energy will be less stable. Some forms which will have less energy will be more stable. So resonating structures do not have same energy. Their energy will vary from one form to another. Some form will be more stable, some form will be less stable. So the form which is less stable, basically having more energy, is less contributor, because there is a less chance of a molecule to be in that state. As I mentioned, in resonance, the forms are interconvertible. They are converting from one form to another all the time in equilibrium. So let's say a molecule tends to show three forms: form 1, form 2, form 3. And assume form 3 is having lesser energy or least energy. That means it is more stable. And assume the first form is having maximum energy. So that means it is least stable. So basically, when the transfer, or when the movement, or when the conversion happens from 1 to 2 to 3, it will stay in the third state or the third form for a longer time, whereas in case of first form, it will stay in a lesser time. So that means first form is being less exposed due to higher energy. It is less stable and will tend to convert into 2 or 3 immediately. So maximum products will be on the basis of, if you target a certain reaction, your form, let me just write it over here if you're getting confused. This is first form, this is second form, this is third form. These all are interconvertible. Okay, this is least stable, and this is more stable. Okay, now assume a reaction is happening. This third form will be present for maximum time because it is more stable. It can sustain itself in that form. Whereas the form 1, when third will get converted into 1 will not be able to sustain itself in that reaction mixture for a long time because it is highly unstable. It will tend to move towards form 2 or form 3. So exposure of a reagent which is going to attack on this molecule, which is showing you 3 different forms. So that reagent will be exposed to form 1 for a very less amount of time, and hence the product formed or the reaction done by form 1 will have lesser product relatively as compared to second and third. So basically what we are trying to say is the one which stays for a lesser time in the reaction mixture will tend to contribute less, more energy, less stability, less stable. That form will not stay in the reaction mixture for a longer time, or that molecule will not stay in that form for a longer time, and hence that particular state will not contribute much in any of the properties of its molecule. That means properties contributed by that state will be relatively lesser because it is not sustainable state. It will quickly try to move towards more stability. Okay, this is what exactly happens. So resonating structure which are contributing less have basically more energy. They are lesser stable, and we also call them minor contributors, not the major contributors. Minor contributors in terms of the properties. So they will contribute very less in the property of the molecule. So basically, if we are comparing two molecules, let's say two different compounds, we will see that which particular compound is forming more resonating structures. So more resonating structures a particular compound can have, more stable it will be. So how can I represent it in the sentence? The resonance hybrid with more resonating structures is more stable. So basically, if I have to compare 2 or 3 different compounds, I will see which one forms more number of resonating structures. More number of resonating structures, more stable that compound would be, or more stable its real hybrid will be. But there is a catch. What is the catch? Let me show you. Okay, let me just compare two compounds and then explain you. Let's say I have taken benzene. So this is my benzene with two structures. One is resonating structure 1 and another is resonating structure 2. If you look at this molecule individually and look at this molecule individually, do you find any difference apart from the positions of the double bond? And marking the carbons on benzene is in our hands. We can mark it either way. So aren't these two structures are completely identical? If you see them individually, if you compare them together, then you can see the positions of the double bonds have changed. But if you see them individually, it is exactly same. There is no difference. Such kind of resonating structures which are identical are called as equivalent resonating structures. Equivalent resonating structures. Whereas if I take the example of buta 1,3 diene, both of these structures I am taking because both we have spoken about. If I have to draw the resonating structure of it, I can draw this resonating structure. So this is resonating structure 1 and this is resonating structure 2. Is there any difference between structure 1 and structure 2? Yes, there is. Double bond position is shifted. That is okay. Apart from that, there were no charges developed in resonating structure 1, but in resonating structure 2 there are charges, positive and negative. The overall neutrality of the molecule is maintained, and that is what we have to maintain also. We cannot make a particular compound negative or positive just by doing resonance. So overall neutrality must be maintained, but charges or poles have got developed. So these two resonating structures are not called as equivalent resonating structures. Equivalent resonating structures means which are identical. Non-equivalent resonating structures are the ones where you can see the difference in the charges, positions of the double bond, and so thing. Okay, so what is our next rule says? Our next rule says the compounds which have equivalent resonating structures, those compounds are highly stable due to this equivalent resonating structure nature. These structures which are equivalent impart extreme stability to the molecule, and hence the number of resonating structures don't matter. If I have a compound A which can have 5 resonating structures but non-equivalent, that means there is a difference in the resonating structures. And if I talk about compound B which has 2 resonating structures but equivalent, so let me tell you, this equivalent resonating structures drastically change the stability of the molecule. They impart extreme stability to the molecule, and hence we will not check at the number here. We will not see, okay, there is a compound A which has 5 resonating structures and hence it should be more stable, or its real hybrid should be more stable. No. In any case, you cannot compete with the molecule having equivalent resonating structures. So no matter it has only 2 resonating structures, but both are equivalent, which drastically improves the stability of the molecule. And hence, if somebody will ask us which is more stable, B is more stable than A. And now here, when we have to compare between 2 compounds, one having non-equivalent resonating structures and one is having equivalent resonating structures, irrespective the number of resonating structures, molecule having equivalent RS will be the most stable one. Okay, so I hope you have got it, what is equivalent resonating structures and what is non-equivalent resonating structures. So again, this is the next point. In some cases, equivalent resonating structures are present. Wherever the equivalent resonating structures are present, stability is especially very high, and it is higher than those molecules also which have more number of RS, more number of non-equivalent RS. Okay, so their number of resonating structures will not matter, but equivalent and non-equivalent will matter. Okay, if you are comparing 2 compounds both having non-equivalent resonating structures, then you will count the number. Which one is showing more resonating structures, and that compound will be more stable. Okay, what basically imparts the stability in the molecule? Just understand this thing. If you have a charged molecule, okay, if you have a charged molecule, negative charge, positive charge, whatsoever, when you are doing resonance, the charge gets distributed among other carbons. Okay, for example, when I talk about CH2 double bond CH single bond CH2 plus, we have already spoken about this species in delocalization when I was talking about conjugation. So when this is the thing, it can actually be written as CH2 plus CH double bond CH2. So basically this molecule is form 1 and this is form 2. The delocalization of pi bond has happened, and now the double bond is formed between second and third carbon, whereas first carbon has got a positive charge. So basically, stay of a charge on a particular carbon has got restricted in time, in terms of time, as well as when you see the overall impact. Earlier, in a particular carbon or in a particular atom, the positive charge or a negative charge or a lone pair was concentrated at that particular atom only. But due to resonance, due to delocalization, it gets distributed in the chain. That means the intensity of the charges gets reduced. Lesser the charge will be on a molecule, or more distributed the charge will be on the molecule. More stable will be the molecule, because individually atoms will be more stable. So if a particular molecule has a concentrated charge and if a molecule has a distributed charge, the distributed charged molecule will have more stability because the intensity of that charge is relatively lesser. Okay, so that is the reason why resonance imparts a stability. Now, what is resonance? We had already spoken. It is basically the gameplay of imaginary structures. What we write, we represent a molecule through our imaginary structures, and those imaginary structures do not give you the complete information of the molecule, but tend to tend to give you some help in terms of reactions, because that is the only way we can write the structures using our hybridization concept. Whereas the real hybrids or the resonance hybrids are the actual structures, but the problem with those structures is we cannot prove it through the hybridization and we cannot represent it in a right way. And probably those structures are not even right way to write a reaction, because you won't be able to prove any reaction through that. 1.5 bond, how will you show how the reaction is taking place? So we can show the reaction with the whole single bond or a double bond, but in between bonds, representation or behavior or reactions cannot be explained, because we have a very limited restricted access to the theory, or our theory is not capable enough to explain all that what a resonance hybrid get. Okay, next is definition of resonance in more scientific terms. Scientific terms, resonance is nothing else but delocalization of pi electrons, as I mentioned, in the parallel p orbitals. Conjugation is resonance, resonance is conjugation. So for conjugation, the mandatory condition is we should have parallel p orbitals. So that's the same condition for resonance also. So delocalization of pi electrons in parallel p orbitals is known as resonance, and our system must be planar. So all the atoms which are participating in the resonance must be planar, basically should be in the same plane, cannot be on the different plane. Okay, so here again I have shown you buta 1,3 diene structure, where I have shown that the electron transfer is happening, shift is happening. One carbon is getting positive charge, another carbon is getting negative charge, and a pi bond is forming in between. Basically, what is happening, your pi electrons which were concentrated at a certain place have got distributed throughout now. Okay, earlier it was between first and second carbon, third and fourth carbon. Then in the second form, they got shifted to second and third carbon, and charges got segregated on first and fourth carbon. So basically, charge separation is happening in the molecule. Charge distribution is happening, pi electrons distribution is happening in the chain. This is the reason why resonance brings stability in the molecule. So basically, distribution of pi electrons in throughout the chain, or a distribution of charges in the wider distance or longer distance, makes the molecule much more stable. So electron density becomes more uniform due to delocalization, which makes the molecule extra stable. Now, as I mentioned, resonance and conjugation goes hand in hand. So what are the conditions when resonance can take place? Resonance can take place only in the conjugated system. What is conjugated system? Where pi electrons get delocalized and the p orbitals which are present should be in parallel to each other, and all the atoms should be all the atoms which are participating in delocalization or conjugation or resonance must be in the same plane. These are the conditions. Now, what all different type of conjugations are possible? Let's see. So there are multiple different ways the conjugation can be defined. So as I mentioned, conjugation is parallel p orbitals, but how we can see this in a molecule, whether these are parallel or not, or whether these are perpendicular to the plane or not, or the atoms are in the same plane or not. So for that, we can also define in a little more easier manner what is conjugation. So your conjugation can be shown on paper through different ways. One is, if in a compound you see the arrangement like where double bond is spaced out with a single bond, and then comes a positive charge, basically double bond, single bond, positive charge. This kind of arrangement is there in a molecule. That means the molecule is in conjugation. Apart from that, double bond, single bond, and negative charge. That negative charge can be on the carbon or can be on any other element also. Okay, then we have an arrangement like where you find pi bond separated by a single bond and then a lone pair. So you can have an atom over there which has lone pair. Okay, so it's like you have CH2 double bond CH, single bond O H. So this kind of structure. So you can see double bond and then single bond and then a lone pair. This kind of arrangement is also called as conjugation. Then you can have double bond, single bond, and a radical. Okay, double bond, single bond, double bond. I showed you this in the diene structure also. So this is conjugation, where you have double bond, alternate double bonds. Sixth is where the lone pair is separated with a positive charge through a single bond. So there is a single bond in between, a lone pair, single bond, and a positive charge. We will be talking about all these cases and you'll see different examples of it. Last one is where you have a negative charge. Basically, a species has a negative charge, then a single bond, and then vacant d orbitals. So these all are the conditions for conjugation, or these kind of representations if you see in a molecule, that means conjugation is present in the molecule and resonance can take place. Now we will go one by one for all of these types and we'll see how resonance exactly take place in them. We will see the orbital diagrams and we will see how delocalization of pi electron takes place in all these 7 setups. Let's start with the first setup, and the first setup is when the double bond is in conjugation with the vacant p orbital. That means you have a double bond, then single bond, and then either the positive charge or vacant d orbital. If we are talking about positive charge, we are basically talking about carbon carrying a positive charge, so basically carbocation. Or if you are not talking about positively charged species, but simply an atom which has vacant d orbital, we are basically going to deal with boron. So boron is the one which has no positive charge, BH3. If you talk about the BH3 structure, it has an empty p orbital naturally present. So if a molecule has, if an atom has a naturally vacant p orbital present, that can also be included in the conjugation. So conjugation is not a concept only for organic, this is there in the inorganic also. Okay, so here when we are saying vacant p orbital, that can be due to the positive charge, or that can be naturally in the atom there is a vacant p orbital which you can use for the conjugation. So this is what we will understand when double bond is in conjugation. Conjugation means is present on the alternate position with respect to the vacant p orbital species. That can be carbon with a positive charge, or can be boron, or any such atom which has vacant p orbital present. So let's see the examples. One example we have already discussed earlier, that is CH2 double bond CH single bond CH2 plus. This example we have already discussed when we were talking about the conjugation earlier. Let's quickly revise the same thing so that you will get into the groove of conjugation, and then it will be easier for us to see other examples also. The first is I'm drawing the orbital diagram. This is the orbital diagram which I'm carrying here in front of me also. This is my CH2 CH CH2 plus. Okay, this I had shown you earlier in this video also, that you have these hydrogens and these hydrogens in one plane, and you talk about the p orbital. P orbitals are which are forming pi bond are in perpendicular to the sigma bonds, and these are parallel to the empty p orbital of the carbon which is present here. So this is empty p orbital, okay, and these are the p orbitals which are involved in the formation of the pi bond. All of these are parallel to each other. All the p orbitals are parallel to each other, but in the perpendicular plane with respect to the sigma bond. So this is exactly the orbital diagram of this species which we have already discussed earlier. Now I told you last time also when I had explained you the conjugation, that what happens is this p orbital which is empty is forcefully try to form a bond with the second carbon which is present in the neighbor of in the neighboring position of it. So this carbon and this third carbon will try to form a new bond, because this third carbon will try to stabilize itself by giving away its positive charge, and it can give away its positive charge only when it will form the bond with something. So it will forcefully try to form the bond with the second carbon. So basically now we want is a new overlap between the second carbon's p orbital and the third carbon's p orbital. Why do we keep a condition that the p orbitals must be parallel? Because to form a new pi bond, these two p orbitals have to overlap. If they are not in parallel to each other, they won't be able to overlap with each other. Okay, so now the second and third carbon's p orbitals want to overlap with each other, but second carbon's valency is already fulfilled. So what will it do? It will break the existing pi bond in such a way that it gets the electron density. Second carbon gets the electron density because it can form the bond with the third carbon only and only if it will have some electron density, because carbon third is already electron deficient. That is positive. This has to be negative. So it will break its bond with the first carbon in a heterolytical manner, so that electron density gets shifted to the second carbon, and now second carbon and third carbon's p orbitals will overlap with each other and will form a pi bond, whereas the first carbon, which was earlier involved in formation of pi bond, will get a positive charge. So this will become an empty p orbital now. This p orbital and this p orbital will overlap now and will form a new pi bond. Okay, so what we can see, the change what we can see is now the first carbon has a positive charge, second and third carbon are forming the pi bond. So what we can see, the pi bond has got shifted from 1 to 2 to 2 to 3. This kind of shifting has happened. So there is no actual shifting happened, but it looks like the shifting has happened, and this is what is called as delocalization of pi electrons. Earlier, the electrons were shared between first and second. Now the electrons pi electrons are being shared between second and third. So movement of pi electrons have happened. This exactly is the delocalization, and this is the resonance in this molecule. So first structure is resonating structure 1 and the another structure is the resonating structure 2. None of these structures are actual structures. These are imaginary structures, but we can draw a real hybrid or resonance hybrid out of it by mixing both of these structures together. So how will I write this? I can write it as CH2 plus CH double bond CH2. This is my RS1, this is my RS2. If I have to combine both of these structures, just you try on your own what exactly will be the resonance hybrid. The sigma bonds will not get affected. So let's write the sigma bond first. Okay, this is my sigma bond structure. Now let's see a pi bond. So pi bond in case of first resonating structure is between first and second carbon, and according to the second structure it is between second and third. So basically it is there throughout in the chain. So I can just represent the movement of pi bond by dash dash dash. So that means for some time it is between first and second, and for some time it is between second and third. Then the positive charge which was on third has got shifted to first. So basically positive charge is also moving. So third is not always positively charged. Third carbon is not always positively charged. It is positively charged for some time, and then first carbon is positively charged for some time. So how do we represent that sometime thing? We represent it through the partial positive charge. So your first carbon and the third carbon will have partial positive charges. So this is my resonance hybrid. This is how we will represent. Okay, because for some time first carbon is carrying positive charge, for some time third carbon is carrying positive charge. So we will represent it by partial positive because they are not completely positive all the time. Okay, this is the resonance hybrid. This is the real hybrid of this molecule. And here is the conjugation. What is happening? This conjugation is nothing else but resonance. Now look at the second example. What we have in the second example, we have taken CH3, CH double bond, CH single bond, CH2. Okay, I'll not be drawing the orbital diagram for all the examples. I have given you one, I have shown you one, and you have to now start imagining it on your own. Okay, so now basically there is a p orbital here, there is a p orbital here, there is a p orbital here. That's how it is. Okay, and again because these p orbitals are in parallel to each other, and this is also the combination of double bond, single bond and plus charge. Just look at it. Isn't this the same combo or the first case what I had taken double bond in conjugation with plus charge? Conjugation means on the alternate position. Okay, so what exactly is going to happen here? This carbon will try to form a double bond with this carbon. For that, let's mark it as first, second, third and fourth. Second carbon will have to break the bond with the third one. So it will break the bond in heterolytical manner so that it can gain a negative charge. The intermediate species will look like this, CH3CH. You won't draw the intermediate species, by the way. So it will be CH, this will be plus, this will be minus, and this and this. Okay, now this p orbital, this carbon's p orbital will have two lone pairs, and this p orbital will be empty. These two will combine, will form a pi bond. So pi bond will form over here, and this third carbon will get a positive charge. This is how exactly the resonating structure will form. So this is my resonating structure 1 and this is my resonating structure 2. So in the resonating structure, what has happened? The charges are maintained. It had plus charge over here. So plus charge has got shifted from first position to third position. And the pi bond has got shifted from second to third to first and second. Now if I have to form the resonance hybrid, how will I form? I will write the sigma bonds as it is. So CH3, CH, CH, CH2, and because the double bond is between second and third in one form and first and second in another form, so I'll show the partial bonding over here, partial bonding between third, second and first, and the plus charge is also not staying forever on first or third carbon, so it is changing from first to third, third to first, so it will be delta positive here and delta positive here. This is how we are going to form the resonance hybrid. Next, look at the next example. What will happen? I have a double bond. See, you have to show the arrows to show the movement of electron from where to where it is going, from where it is breaking and where it is moving and forming a new pi bond. All that you have to show. Without arrows, all the things what you're writing are wrong and will not be considered. This is an important topic for the school exam also. So if you're not showing it with the arrows, first of all, you will yourself get confused. Secondly, your answer will not be acceptable and you will definitely make a mistake in your answer. Okay, so it's always better to show the movement using the arrow. So here in this case, what we have, this is my molecule with a plus charge. So again, double bond, single bond plus charge on the alternate position. This is conjugated system. Now what will happen? This carbon, let me use a different pen. This carbon and this carbon, both of these carbons will form a new pi bond by breaking the existing one. So existing one will break. Let me draw it a little bigger. So this is the one. Okay, so existing one will break. And how will it break? This carbon has a positive charge, so this should be negative to get a pi bond, and this should become positive. So basically bond will break heterolytically. This carbon will get a negative charge and this carbon will get a positive charge. This negative and positive will form a pi bond, and we will not show this plus and this minus. So pi bond has got shifted from this position. Let's mark the positions. This is position 1, 2 and 3. Between 2 to 3 it was earlier. Now it has moved to 1 and 2, and the plus charge has shifted from first position to third position. If I have to form the resonance hybrid, this is how I'll be forming. So double bond is in between first to 3. So all the 3 carbons are sharing the double bond. So dash 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 to represent a double bond, and plus charge is staying on first carbon and the third carbon. So partial positive charge over there. This is your resonance hybrid, and these are 2 resonating structures. Now look at the next example. So in the next example, okay, I'll do one thing. I'll draw it on my own on a board so that you'll be able to understand much better. The structure is something like this. I think this is right. Alternate, and this is the molecule. Okay, so we have to see whether we have a conjugated system or not. So look at this double bond, single bond plus charge. There is a conjugate system over here, so their conjugation will happen. Okay, now let's go. So first we will deal with only this conjugation. Let me mark the carbons. Assume this is carbon 1, this is 2, this is 3. This is just a representation. We are not marking it for naming the compound or anything like that. This is just for your reference, so that I can tell this carbon rather than this. I can say carbon 1, carbon 2, carbon 3. Okay. So now first carbon has a plus charge, second and third has a pi bond. So what will I do? The second carbon will take the electron density to form a new bond between first and second carbon, and the third carbon will become positive. That's how the delocalization will happen. I hope till now you would have understood this part at least, how delocalization is happening when you have a plus charge and a double bond on the alternate positions. So this double bond will remain as it is. This will become double bond. Have I drawn it right? Yeah, and this carbon 3 will get a positive charge. Okay, now look at this positive charge. This positive charge is in conjugation with this pi bond. So will it stay here? No, it will move further. If it gets a chance to move further and get further delocalized, it will get further delocalized. So this pi bond will also break heterolytically by giving an electron pair to this carbon. So this will be a negative carbon, this is a positive carbon. They will form a new pi bond, and this carbon will get a positive charge. So how can I show it? Please understand it carefully. So pi bond has moved over here and plus charge has moved over here. This is resonating structure 1, this is resonating structure 2, and this is resonating structure 3. Okay, now can I see furthermore conjugation? Yes, there is a pi bond over here and single bond and plus charge. So what will happen? This pi bond will break in such a way that this carbon gets a negative charge. This negative and positive carbon will form a pi bond, and this carbon will become positive. So this will be like this. It's a chain effect. It's basically one by one. It is shifting from one place to another, and the plus charge has come over here. This is my resonating structure 4. Right? So this is how exactly the resonance is gonna happen. Even if it's throughout the chain, it will distribute in the whole chain, and that is what we exactly say. More the distribution of pi electrons or the positive charge or the negative charge is, more stable your molecule would be. So these are all resonating structures. None of the structure is actually representing the molecule. They are just representing one part of a molecule which will represent certain set of reactions. Now if I have to show the resonance hybrid of it, let's draw all these single bonded structures directly. These are all sigma bonded things. Now look at the carbon. So first carbon, second carbon, third carbon, fourth, fifth, sixth, seventh. All, if you look at all the positions, basically all of them have pi bond at some or other point. So let's draw the pi bonds through the dash, because these pi bonds are traveling throughout. Okay, just look at it. You can check if, just in case you are getting confused or you feel that no, it's not like that, you can put the numbers in each structure and see whether it's coming between all the carbons or not. I mean, between second, fourth, fifth, sixth. So it is traveling throughout. The double bond of pi electrons are traveling throughout in the chain, and the positive charge also. So positive charge is on the first carbon in one structure. So let's put a partial positive. Then it's on the third carbon. So let's put a partial positive over here. Then it is on the fifth carbon. So let's put a positive charge over here. And then it's on the seventh carbon. So let's put a positive charge over here. So this is my resonance hybrid. That's how exactly you have to draw and you have to write. Please understand this very, very neatly. You have to draw it in your notebook very neatly. You have to represent it. The moment you will start scribbling in your notebook, the moment you will start just imagining without writing it on in your notebook, you just think on your own, and then you don't pick your pen, and then you're just thinking and assuming, yeah, my answer is right. I can guarantee you, at least in the beginning, not once you have become pro, but in the beginning you will end up doing a lot of mistakes, and then you'll end up getting confused. Okay, so here when you are practicing resonance, you should write everything and you should show all the arrows. Make your diagrams as clear as possible so that you can understand where you have made a mistake, if there is any. Okay, so now let's see the next example. So this example we have just discussed. Next is the benzene with CH2. Benzene with CH2 and plus charge. So here also again you will have to see, you have to look at it very, very carefully. So here what is happening, again this double bond and this plus charge is on the alternate position. This is in conjugation. This double bond will be broken in such a way that this carbon will get a negative charge and the new pi bond will form. So new pi bond has formed over here and plus charge has come over here. This is your resonating structure 2. Earlier was resonating structure 1. Then this pi bond will break in such a way that this carbon will get a negative charge, and there is a new pi bond formation between this negative carbon and this positive carbon, and the plus charge will shift at this position. So this is exactly what I have done. Plus charge has got shifted over here. Then what will happen? This pi bond will break in such a way that this carbon will get a negative charge, right? And then this carbon and this positive carbon will form a pi bond, and this will get a positive charge. So this is what exactly we have drawn in the next form. Then again the movement of electron will happen in such a way that this pi bond will break. This carbon will get a negative charge. This positive carbon and this negative carbon will form a pi bond, and this carbon will gain a positive charge. This is what exactly we'll get. So we have reached to almost the same state where the CH2 had a positive charge, but look at the positions of the double bonds. The position of double bonds have got changed. So we have got 5 resonating structures. Resonating structure 1, 2, 3, 4 and 5. So this molecule has 5 resonating structures. Try drawing it on your own rather than just copying it from here, because I can explain you, I know the things. I mean, you don't know the things, you have to write and see whether you are getting it or not. More you will write, more you will understand. So resonance hybrid, how it will be, double bond is traveling throughout in the ring as well as in the in the alkyl chain. So you will put a dash 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 over there, and which all positions have got a positive charge, all those positions you will put a partial positive charge. Next is resonance in cyclopropanil cation. This is a cyclopropanil cation. There is a double bond on the alternate position with plus charge. What can happen? This bond can break in such a way that the electron comes here, electron pair comes here, and the new pi bond forms over here, and the plus charge shifts over here. This can happen, right? So I'm just rubbing it off. Okay, so this is exactly what we have done. So this I have shown it over here. Okay, apart from that, what else could have been happen? This could have moved over here, so this would become negative. Positive charge will come over here, and a new pi bond will form over here. So this is exactly what have been drawn. So both of the structures are fine. I mean, the electron density can go there also and go here also. Both the structures I have drawn. This is resonating structure 1, this is resonating structure 2, and this is resonating structure 3. Now, if you look at these 3 structures individually, can you find any difference? I mean, you can start marking or numbering the carbon from any position. You look with respect to each other, you can see the double bond and the plus charge is moving, but can you see individually any difference? If you treat them individually, will you find any difference in terms of charge segregation or the pi bond? No. So all the 3 structures are exactly same. Okay, though when you compare with each other, yeah, actually the pi bond is moving, and such structures I told you earlier also are called as equivalent resonating structures. So the compounds, the cyclic structures which tend to show the equivalent resonating structures and the charge is equally distributed throughout the ring. If you see this, let's mark it first, second and third. So if I'll draw the resonance hybrid of it, how the resonance hybrid will look like, this will look like this. Just see over here, okay? So there is a partial positive charge here, partial positive here, partial positive here. But what exactly is the amount of this partial positive? It is equally distributed between first, second and third carbon. So I can write it as 1 by 3 positive charge, 1 by 3 positive charge and 1 by 3 positive charge. So isn't this positive charge being equally distributed among all the carbons of the ring? Yes, it is. And when in a chain, double bond is equally traveling throughout and the charges have been equally distributed between all the atoms, such compounds are called as aromatic compounds. So if you remember, we had discussed some conditions to explain which kind of compounds can be aromatic. So this is also one more condition, that your charge should be equally distributed throughout the ring. Okay, and your double bond should also be equally distributing or equally traveling in the whole ring, then only the compound will be called as aromatic. So basically it should have equivalent resonating structures, equal charges on all the carbons, and the pi electron should be equally distributed in the whole ring, then the molecule will be called as aromatic. So this is my aromatic molecule with 4n plus 2 pi condition it is fulfilling, where the number of pi electrons are 2 pi electrons. This case also we had discussed at that time also when I was discussing aromatic compounds, and here again there is a little additional information which we have added. So let's see the next set of compounds. So here equal dispersion of charge has happened in the molecule, charge as well as the pi electrons have been equally distributed in the whole ring, and that is why the compound will be called as aromatic. Let's see one more example of aromatic compound. So if you look at this compound, how many electrons are there? 6 electrons are there, 6 pi electrons, which fulfills the condition for aromaticity. Apart from that, we have to see, that's one condition. Okay, second condition is all the atoms of the cycle should be planar, or it should be in the same plane. So all of these are sp2 hybridized, all are in the same plane. Okay, third condition is the charge should be equally distributed throughout and the pi electron should be equally distributed. So that is what we are going to check, whether it is going to get equally distributed or not. Here is my plus charge and here is my double bond. I can travel from here or I can travel from here, anywhere I can travel from. So this plus charge and this pi bond is in the alternate positions and this is in conjugation. So first of all, what will happen? The pi bond will break, electron will come on the second carbon. Second and the first carbon will try to form a pi bond and the plus charge will shift on the third carbon. Okay, very usual behavior. Now next, this plus charge, this pi bond between 5 and 4 will shift or will break in such a way that the fourth carbon will get electron density. This plus third carbon and minus 4 carbon will form a pi bond and plus charge will shift to the fifth carbon. So this is how it will look like. Fifth carbon by plus charge has got shifted and the pi bond is between third and fourth carbon. Now again, sixth and seventh carbon, the pi bond will break in such a way that sixth carbon will get the electron density. Electron rich sixth carbon and electron deficient fifth carbon will form a pi bond and seventh carbon will get a positive charge. So this is how it will look like, right? Next, what can happen again? Then again, this plus charge on the seventh carbon and the second carbon pi bond is in conjugation. So what will happen? The bond between first and second carbon will break in such a way that the first carbon gets electron density, seventh carbon is electron deficient, both of them will make a pi bond and the plus charge will go to the second carbon, right? So we keep on doing the resonance till the time we reach to the original state. Okay, so not original state, basically we should get the different structures every time, or it should go through all the carbon and should distribute the electron density wherever is possible. Then only we stop making the resonating structures. Okay, so this is what we have got by shifting the electron density from second to first. The pi bond is formed between seventh and 1 and second got a plus charge. Now this plus is again on the alternate position with the fourth. Now how do you know where to stop? Basically now plus charge should be moving to each and every carbon. That's what we are checking over here, whether it can move to all the carbons or not before getting the exact same structure what it had earlier. Okay, so here second and third carbon, this will break, the bond will break in such a way that second and third will form the pi bond again and fourth will get a positive charge. Okay, then again what will happen? The bond between fifth and sixth will break in such a way that fourth and fifth will form a pi bond and sixth will get a positive charge. So this is the structure which will be forming. Then again, what will happen? Plus charge of sixth is in conjugation with the pi bond which is on first and seventh, and the bond will break in such a way that 7 will get the electron density, bond will form again between 6 and 7, and the plus charge will come to the first position. So this last compound and the first compound is exactly same. And apart from that, what we have seen, the pi bond has gone to each and every carbon also, and the plus charge is also gone to each and every carbon. So basically plus charge is equally distributed among all the carbons, and the pi electrons are also equally distributed among all the carbons. When I'll draw the resonance hybrid, you'll be able to see plus charge was at first carbon, then went to third, then went to fifth, then went to seventh, then went to second, fourth, sixth. So basically the plus charge has traveled everywhere, even the double bond has traveled everywhere. So it is distributed throughout in the ring. All the positive charge is equally distributed among all the carbons, and the double bond is completely, or pi electrons are also completely distributed among all the carbons in this compound. So this compound is aromatic. Apart from this can show resonance, we can also say this is an aromatic compound. So this is one of the mandatory conditions, that the charge should be equally distributed and pi electron should be equally distributed in the ring when you have to tell the compound is aromatic or not. Next, and the last compound which we'll discuss for this case is where we have no carbocation, we have BH2. I had told you we can take an element over here, any other element also which has naturally a vacant p orbital, and then it will show you the conjugation. So it is not necessary to have a plus charge. You can have a compound, you can have an atom over there which has empty p orbital, because basically conjugation has to be done with the empty p orbital. We need empty p orbital over here, which is in parallel with the p orbitals which are making pi bond, nothing else. So it doesn't matter whether it had earlier an electron, it never had an electron, so that really doesn't matter. So how the conjugation will happen over here, this is the orbital diagram. Exactly same, only thing is the plus charge is not there, and this is not carbon, this is boron. So what will happen, this pi bond will break in such a way that the electron density will shift to the second carbon, and the second carbon will try to overlap with the boron and will form a pi bond. Now when it will give the pi bond, when it will form the pi bond, just understand one thing. It has received 2 electrons, out of which 1 electron it will give to boron to form a pi bond. Boron doesn't have a pi bond. It is just giving its one of the electrons to the pi bond. In case of carbocation, carbon already was carrying a positive charge. Then it got an electron from the second carbon, and that positive charge gets nullified. That's what exactly happens when the carbocation is there. Boron doesn't have any positive charge. So when it will get an extra electron to form a pi bond from the carbon, then what will happen? This boron has got an excess of electron, which is not its own. It has got it from carbon to form a pi bond, and hence it will gain a negative charge on itself. Whereas the carbon, which was earlier involved in the pi bonding, and the bond broke heterolytically and the second carbon took the whole density, this first carbon will gain what? Positive charge. So overall neutrality of the molecule will be maintained. Just again understand what I'm trying to tell you. I have CH2 double bond CH, single bond BH2. Now what has happened? This first of all got converted into CH2 plus CH2 electrons and minus, and then BH2. Okay, till now only positive negative over here. Now after this, what will happen? This pair of electron, this second carbon will share with the boron to form a pi bond. So basically boron will get an extra electron which is not its own. It has got it from carbon. So that is the reason when the pi bond will form between carbon and boron, boron will get a negative charge. This carbon has already got a positive charge over here, and this carbon is anyways neutral. So this is what exactly will be formed. So this you have to understand why boron has got a negative charge on it. When you will try to draw the resonance hybrid, you will mix both the molecules. This is resonating structure 1 and this is resonating structure 2. So both will mix. Boron will have a partial negative charge, carbon will have a partial positive charge, and double bond is distributed throughout. Okay, so these are some examples which I have explained to you. You try some of the compounds on your own. Okay, so these are the compounds given. Stop the video, try them out on your own, and then we will discuss the answers. I hope you guys are done. Let's quickly see. The first compound, this was the resonating structure given. This was the compound given. So this is resonating structure 1. How the shifting of the bond can happen? This bond will break heterolytically. Negative charge will come on this carbon. This negative and positive carbon will form a pi bond, and plus charge will shift to this carbon. So this is how exactly it will look like. Okay. The two resonating structures, resonance hybrid will be something like this. There will be a delta positive here and delta positive here. Okay, next compound, there is a positive charge on this carbon and this carbon and this carbon. These are the 3 carbons which are involved in conjugation. So there is a pi bond over here. So this pi bond will break heterolytically. This will gain a negative charge. This carbon will gain a negative charge. This negative carbon and this positive carbon will form a pi bond, and the plus charge will come over here. So this is how it will look like. Next, this is the compound. This plus charge is in conjugation with this double bond. This double bond will break heterolytically and a new pi bond will form over here, and the plus charge will form here on this carbon, which will be this. Now this plus charge is in conjugation with this pi bond. This pi bond will further break heterolytically, electron density will come here. So this will look like this, and the positive charge will be gone to this carbon, so it will be here. This is my 3 resonating structures: resonating structure 1, resonating structure 2, resonating structure 3. Right? Next, look at this compound. So in this compound I have a plus charge over here, and there is a double bond over here, so this will break, its electron density will come on this carbon will become positive, and here we will get a new pi bond. So this is how exactly look like. But can there be further conjugation possible? It can be backwards only. I mean, this plus this breaks down here and forms the same thing again like this. But is it possible with this double bond? It is not possible with this double bond, because this is not in conjugation. This is pretty far. This is not on the alternate position. So the resonance will not happen with this double bond. It will stop here itself. So conjugation is possible only in this part. This part will not be involved even if there is a double bond present over here. Why it will not involve? Because this is not on the alternate position. This is not in conjugation. Okay, so here we are done with the case number 1, when the double bond is in conjugation with empty p orbital. That empty p orbital can be a positively charged species also, or can be a naturally empty p orbital also. Now you would have understood how the resonance takes place in such molecules, what is aromatic compounds, how the resonance make a compound aromatic, what all conditions are required. This is only case 1. We have not done rest of the cases. Rest of the cases we will discuss in the next class. First, go through this, digest this, try to solve some questions or these examples on your own, and then we will move to the next set of conjugation cases, because at that time I'll be a little more faster, and I'll hope that you will understand everything well, because you have gone through. I have taken a good amount of time in explaining the conjugation and resonance. So next set of examples will be a little faster. So we will do them in the next class, not this class. Okay, go through it properly and solve each and every example which I have told you on your own by writing it on your notebook. Do not imagine, do not do the imaginary calculations. You will end up doing mistakes. This is something which I'm repeating again and again, because this is a usual problem with the students, that they try to imagine everything in the beginning. In the beginning, you better write it, and once you get the whole thing properly, the concept and how does it work, then you anyways have to imagine when you'll go for a competitive exam, because at that time you won't have luxury of time to write, draw, and then figure out the answer. Okay, till then, bye bye.